Welcome to Data Warehouse Overview. After watching this video, you will be able to define a data warehouse, identify data warehouse use cases, and list the benefits of a data warehouse. A data warehouse is a system that aggregates data from one or more sources into a single central consistent data store to support various data analytics requirements. Let's take a closer look at data warehouse analytics. Data warehouse systems support data mining, including the application of artificial intelligence and machine learning. Data transformation during the ETL process speeds front-end reporting, delivering critical information fast. Data warehouses enable online analytical processing, known as OLAP, which provides fast, flexible, multidimensional data analysis for business intelligence and decision support applications. Traditionally, data warehouses have been hosted on-premises within enterprise data centers, initially on mainframes and then on Unix, Windows, and Linux systems. Data warehouse appliances emerged with the growth of more extensive data volumes in the 2000s. These appliances consisted of a pre-integrated bundle of specialized hardware and optimized data warehousing software that reduced large-scale data warehousing management overhead. In the last decade or so, with exponential amounts of data being generated and stored in the cloud, cloud data warehouses, frequently called CDWs, have gained popularity, where organizations don't purchase hardware or install warehousing software. Instead, organizations access data warehouses as a scalable pay-as-you-go service. Okay, now that you can define what a data warehouse is, identify where data warehouses exist, and understand their basic structure and outputs, let's examine what organizations use data warehouses. Data warehouses are a part of almost every industry, including e-commerce, transportation, medical, banking and fintech, social media, and governments. But why do these types of organizations use data warehouses? Let's learn more. Retail and e-commerce organizations use data warehouses to analyze and report on sales performance. These organizations also apply machine learning-assisted shopping that provides shoppers with relevant recommendations that drive additional sales. By applying artificial intelligence to patient data, healthcare providers can access the most recent insights and use that information to diagnose and treat their patients with greater accuracy. BI capabilities enable transportation providers to optimize routes, travel times, equipment needs, and staffing requirements. Financial tech organizations, including banking, apply data analytics to evaluate risks, detect fraud, and cross-sell services. Social media organizations need analytic capabilities that can quickly measure ever-changing customer sentiment and project product sales. Governments apply business intelligence to analyze and evaluate citizen-focused programs and assist with policy change decisions. So, what are the benefits of a data warehouse? Data warehouses enable organizations to centralize data from disparate data sources, such as transactional systems, operational databases, and flat files. Data integration, removing bad data, eliminating duplicates, and standardizing data creates a single source of truth that results in better data quality for analysis. A single source of truth empowers users to leverage all the company's data and access that data more efficiently. In addition, separating database operations from data analytics generally improves data access performance, leading to faster business insights. Next, large-scale BI functions such as data mining, artificial intelligence, and machine learning tools facilitate smarter decisions by data professionals and business leaders. These capabilities build on each other to give organizations the means and opportunity to realize competitive advantages and gains. In this video, you learned that a data warehouse is a system that aggregates data from one or more sources into a single consistent data store to support data analytics. Data warehouses support data mining, AI and machine learning, OLAP, and front-end reporting. And finally, data warehouses and BI help organizations improve data quality, speed business insights, and improve decision-making, all of which can result in competitive gains.
Welcome to Popular Data Warehouse Systems. After watching this video, you'll be able to categorize popular data warehouse systems, list some of the more popular data warehouse vendors and their warehousing offerings. Most data warehouse systems are supported via one or more of three platforms. First are appliances, which are pre-integrated bundles of hardware and software that provide high performance for workloads and low maintenance overhead. Other vendors support cloud deployments only, offering the benefits of cloud scalability and pay-per-use economics, and in many cases deliver their data warehouses as fully managed services. Some warehouse offerings have traditionally been available as software, installed only within on-premises environments. But in recent years, most of these vendors now offer cloud-deployed data warehouse systems. Let's view an unranked list of popular data warehouse systems and learn more about them. Let's begin with appliance data warehouse system solutions such as Oracle Exadata. An organization can deploy this data warehouse solution as part of an on-premises installation or via Oracle Public Cloud. Oracle Exadata features built-in algorithms and runs all types of workloads, including OLTP, data warehouse analytics, in-memory analytics, and mixed workloads. IBM Netezza is another warehousing appliance. You can deploy IBM Netezza on IBM Cloud, Amazon Web Services, Microsoft Azure, and private clouds using the IBM Cloud Pak for Data System. IBM Netezza is widely recognized for its data science and machine learning enablement. Next, let's turn our attention to some of the more recognized cloud-based data warehouse systems providers. Amazon Redshift uses Amazon Web Services specific hardware and proprietary software in the cloud for accelerated data compression and encryption, machine learning, and graph optimization algorithms that automatically organize and store data. Up-and-coming Snowflake offers a multi-cloud analytics solution that complies with GDPR and CCPA data privacy regulations. Snowflake advertises its always-on encryption of data in transit and at rest. Snowflake is FedRAMP moderate authorized. Next, Google BigQuery describes its data warehouse system as a flexible multi-cloud data warehouse solution. Google reports data warehouse uptime of 99.99% and delivery of sub-second query response times from any business intelligence tool. Google BigQuery's system specifies petabyte speed and massive concurrency to deliver real-time analytics. Now, let's check out the vendors that provide both on-premises and cloud-based data warehouse systems. Microsoft Azure Synapse Analytics offers code-free visual ETL/ELT processes to ingest data from more than 95 native connectors. Azure Synapse Analytics supports data lake and data warehouse use cases and supports the use of T-SQL, Python, Scala, Spark SQL, and .NET for both serverless and dedicated resources. Teradata Vantage takes a slightly different approach. Teradata Vantage advertises its multi-cloud data platform for enterprise analytics that unifies data lakes, data warehouses, analytics, and new data sources and types. Teradata Vantage combines open source and commercial technologies to operationalize insights and deliver performance for mixed workloads with high query concurrency using workload management and adaptive optimization. For support, Teradata provides a single point of contact for operational task services, including monitoring, change requests, performance tuning, security management, and reporting. IBM DB2 Warehouse is widely recognized for its scalability, massively parallel processing capabilities, petaflop speeds, security features, and 99.99% service uptime. IBM DB2 Warehouse provides a containerized scale-out data warehousing solution. You can move workloads where needed, including the public cloud, private cloud, or on-premises, with minimal or no changes required. Vertica, another known hybrid cloud data warehouse system, provides multi-cloud support for Amazon Web Services, Google Microsoft Azure, and on-premises Linux hardware. Vertica reports fast multi-GB transfer rates, scalable, elastic compute and storage, and notable system fault tolerance when using Eon mode. Oracle Autonomous Data Warehouse runs in Oracle Public Cloud and on-premises with support for multi-model data and multiple workloads. Oracle describes its system as built to eliminate manual data management and reports that they provide extensive automated security features, including autonomous data encryption both at rest and in motion, protection of regulated data, security patch application, and threat detection. In this video, you learned that data warehouse systems can include appliances, exist on-premises, exist in the cloud, or use a combination of these deployment options. Popular data warehouse vendors include Oracle, Teradata, Vertica, Google, IBM, Microsoft, Snowflake, Amazon, and others. Welcome to Selecting a Data Warehouse System. After watching this video, you'll be able to identify criteria that organizations can use to evaluate data warehouse systems, describe key considerations for each data warehouse selection criterion, summarize how organizations decide between on-premises or public cloud data warehouse system, and list the various types of warehouse costs. Let's look at the criteria businesses use to evaluate data warehouse systems, including features and capabilities, compatibility and implementation considerations, ease of use and skills, support considerations, and various costs. One of the primary data warehouse features or considerations for an organization is location. Data warehouses can exist on-premises, on appliances, or on one or more cloud locations. To select a location, organizations must balance multiple demands related to data ingestion, storage, and access. For some organizations, securing their data is their highest priority, requiring a mandatory on-premises solution. Multi-location businesses that grapple with data privacy requirements such as CCPA or GDPR need on-premises or geo-specific data warehouse locations. Each organization balances security and data privacy requirements with the need for speed that delivers critical, profit-producing business insights. Organizations will also want to consider features and capabilities related to architecture and structure. Is the organization ready to commit to a vendor-specific architecture? Does the organization need multi-cloud installation, such as multiple data warehouses in multiple locations? Does the solution scale to meet anticipated future needs? What data types are supported, and what types of data does the organization ingest? If your organization currently analyzes dark data or is planning for the implementation of using semi-structured or unstructured data, you'll want a data warehouse system that supports these data types. And an organization that processes big data needs a system that supports both batch and streaming data. Capabilities that affect the ease of implementation include data governance, data migration, and data transformation capabilities. With the data warehouse system in place, how easily can the organization optimize and re-optimize system performance as needs change? Another consideration is user management. With more organizations implementing a zero-trust security policy because of expensive data breaches, implementing programs that manage and validate system users is mandatory. And notifications and reports are essential for organizations to correct errors and mitigate risks before minor issues become larger problems. Let's explore ease of use and skills. Does your organization's staff have the skills needed to implement a specific data warehousing vendor's technology? And if not, how quickly and easily can they gain those skills? Complex, large data warehouse deployments can require additional work from your implementation partner, so their expertise also greatly matters. Finally, do the technology and engineering staff who architect, deploy, and administer front-end querying, reporting, and visualization tools have the skills needed to configure your new system quickly? Next, let's review some support considerations. Support is essential and can become frustrating and expensive if not well planned for. You might find that by using a single vendor, you can leverage one highly accountable, responsible source, potentially saving you time, money, and frustration. You'll also want to verify the availability of service-level agreements for uptime, security, scalability, and other data warehouse system issues. Validate the vendor's support hours and channels, such as by phone, email, chat, or text. Finally, does the vendor offer self-service solutions and an active, rich user community? After all this analysis, it's time to evaluate and compare costs. When calculating costs for a data warehouse system, consider more than the initial costs. Consider the total cost of ownership, or TCO, for running systems for several years. TCO includes infrastructure such as compute and storage costs, whether on-premises or on cloud, software licensing, or in case of cloud offerings, their subscription or usage costs, data migration and integration costs for moving data into the warehouse and pruning and purging as required, administration costs related to system management and personal training, and recurring support and maintenance costs paid to the warehousing vendor or implementation partner. In this video, you learned that businesses evaluate data warehouse systems based on features and capabilities, compatibility and implementation, ease of use and required skills, support quality and availability, and multiple cost considerations. An organization might need a traditional on-premises installation to adhere to data security and privacy requirements. Public cloud sites offer organizations the benefits of economies of scale, including powerful compute power and scalable storage, resulting in flexible price-for-performance options. And, when selecting a data warehouse system, consider the total cost of ownership, including infrastructure, compute and storage, data migration, administration, and data maintenance costs in your calculations. Welcome to IBM DB2 Warehouse. After watching this video, you'll be able to describe key features of the IBM DB2 Warehouse, list IBM DB2 Warehouse use cases, and list key pipeline tool capabilities and integrations with DB2 Warehouse. IBM DB2 Warehouse is a complete data warehouse solution that offers a high level of control over your data and applications. DB2 Warehouse is easy to deploy within containerized environments such as Docker. DB2 Warehouse is a highly flexible data warehouse for client-managed, on-premises, cloud, and hybrid environments that scales automatically with massively parallel processing, known as MPP, to support containerized deployments. DB2 Warehouse comes pre-packaged with access to machine learning algorithms and utilizes in-database business analytics for speed. DB2 Warehouse enables you to automatically generate data schemas and seamlessly transform and load unstructured data sources into a structured format for analysis. DB2 Warehouse speeds queries using BLUE acceleration, which includes in-memory SQL columnar processing, data skipping, and, as mentioned before, a massively parallel processor cluster architecture that speeds complex queries. DB2 Warehouse supports your AI analytics needs. DB2 Warehouse comes with dashboards for monitoring performance and reporting issues. Some examples of included widgets are hardware and software issue counts, database alerts, and the amount of allotted storage used. You can also view a breakdown of how much time is spent in different states, such as waiting for locks and time to execute SQL queries, and a table of details regarding any database alert events. There are many other widgets available, such as System and Data Server CPU utilization history, and others. Some of the use cases that DB2 Warehouse is well suited for include elasticity or high scalability requirements. cloud, on-premises, or hybrid hosting, consolidation and integration of disparate data sources, rapid development of line-of-business analytics products such as data marts, management of sensitive or regulated data, and storage of older, colder structured SQL data. DB2 Warehouse supports a range of clients and plugins, including Java Database Connectivity, or JDBC, Node.js, Spring, Python, R, Go, Spark, and Microsoft Visual Studio. IBM DB2 Warehouse, with its integrated Apache Spark cluster, can be partitioned and deployed across a cluster of machines. You can submit Apache Spark jobs through stored procedures to run against DB2 Warehouse, extending your analytical reach. You can use RStudio to analyze, wrangle, model, and visualize your data with DB2 Warehouse. For example, you can create your own Docker image that contains RStudio and all the packages and drivers you need to connect to DB2 Warehouse. You can even develop applications that run R code, integrated with DB2 through a REST API. DB2 Warehouse also has a range of commonly used open-source drivers available on GitHub in the IBM DB repository. For example, under Popular Repositories, you can find the Python IBM DB package, which provides a Python interface for connecting to IBM DB2. In this video, you learned that IBM DB2 Warehouse is a cloud-ready, highly flexible data warehouse platform. Key features of IBM DB2 Warehouse include speed, scalability, automated schema generation, and built-in machine learning. Use cases include data integration and rapid development of data marts, and DB2 Warehouse integrates with JDBC, Apache Spark, Python, and RStudio.
Welcome to Data Mart's overview. After watching this video, you will be able to define what a data mart is, give examples of data marts, compare data marts to transactional databases and enterprise data warehouses, and describe data pipelines for loading data marts. A data mart is an isolated part of the larger enterprise data warehouse that is specifically built to serve a particular business function, purpose, or community of users. For example, the sales and finance departments in a company may have access to dedicated data marts that supply the data required for their quarterly sales reports and projections. The marketing team may use data marts to analyze customer behavior data, and the shipping, manufacturing, and warranty departments may have their own data marts. So, what are data marts used for? Data marts are designed to provide specific support for making tactical decisions. As such, data marts are focused only on the most relevant data, which saves end users the time and effort that would otherwise be spent searching the data warehouse for insights. The typical structure of a data mart is as follows. It is a relational database with a star or more often a snowflake schema, which means it contains a central fact table consisting of the business metrics relevant to a business process, which is surrounded by a related hierarchy of dimension tables that provide context for the facts. Let's look at some typical differences between three types of data repositories: data marts, transactional databases, and data warehouses, starting with data marts and databases. Both data marts and data warehouses are online analytical processing, or OLAP systems, that are optimized for read-intensive queries and operations, whereas transactional databases are online transaction processing, or OLTP systems, that are optimized for write-intensive queries and applications. Data marts use transactional databases or data warehouses as data sources, while in transactional databases, operational applications such as point-of-sale systems serve as the sources of data. A data mart stores validated, transformed, and cleaned data, while a database will have raw data that has not yet been cleaned. Data marts accumulate historical data that can be used for trend analysis, while transactional databases may not always store older data. A data mart is much like a data warehouse, except that it has a smaller tactical scope. Data warehouses broadly support the strategic requirements of the enterprise. Data marts are lean and fast compared to data warehouses, which can be very large and hence can be slower. There are 3 basic types of data marts: dependent, independent, and hybrid. The difference between these 3 kinds of data marts depends on their relationship with the data warehouse and the sources used for supplying each of them with data. Dependent data marts draw data from the enterprise data warehouse, while independent data marts bypass the data warehouse and are created directly from sources, which may include internal operational systems or external data from vendors or other sources outside the enterprise. Hybrid data marts only depend partially on the enterprise data warehouse. They combine inputs from data warehouses with data from operational systems and other systems external to the warehouse. Dependent data marts offer analytical capabilities within a restricted area of the enterprise data warehouse. Thus, they inherit the security that comes with the enterprise data warehouse. And since dependent data marts pull directly from the data warehouse, where data has already been cleaned and transformed, they tend to have simpler data pipelines than independent data marts. Independent data marts differ from dependent data marts because they require custom extract, transform, and load data pipelines to carry out the transformation and integration processes on the source data, since it is coming directly from operational systems and external sources. And independent data marts may also require separate security measures. Whatever the type of data mart you may have, its purpose is to provide end users with relevant data when they need it, accelerate business processes by providing efficient query response times, provide a cost-efficient method for informing data-driven decisions, and ensure secure access and control over your data. In this video, you learned that a data mart is an isolated part of the larger enterprise data warehouse that is specifically built to serve a particular business function, purpose, or community of users, is designed to provide specific, timely, and rapid support for making tactical decisions, and typically has a star or snowflake schema. You also learned that unlike an OLTP database, an OLAP data mart stores clean and validated data and accumulates historical data. And you can categorize data marts in terms of their dependence on the enterprise data warehouse. A data mart can be completely dependent on the data warehouse, a completely independent standalone mini data warehouse, or a hybrid of the two. Welcome to Data Lake's overview. After watching this video, you will be able to define what a data lake is, list benefits of using a data lake, and compare data lakes to data warehouses. A data lake is a storage repository that can store large amounts of structured, semi-structured, and unstructured data in their native format, classified and tagged with metadata. You would opt for a data lake if you generate or have access to large amounts of data on an ongoing basis, but don't want to be restricted to specific or predefined use cases. Data lakes are sometimes also used as a staging area for transforming data prior to loading into a data warehouse or a data mart. Let's break this information down a bit. A data lake is a data repository that can store a large amount of structured, semi-structured, and unstructured data in its native format. You do not need to define the structure and schema of data before loading the data into the data lake. You do not even need to know all the use cases for which you will be analyzing the data. A data lake exists as a repository of raw data straight from the source to be transformed based on the use case for which it needs to be analyzed, which does not mean that a data lake is a place where data can be dumped without governance. A data lake is also a reference architecture that is independent of technology. Data lakes can be deployed using cloud object storage, such as Amazon S3. Or large-scale distributed systems such as Apache Hadoop used for processing big data. You can deploy data lakes on relational database management systems as well as NoSQL data repositories that can store very large amounts of data. Data lakes offer a number of benefits. Data lakes can store all types of data, including unstructured data, such as documents and emails, semi-structured data, such as JSON and XML files, and structured data from relational databases. Scalability is another data lake benefit. Data lakes can make use of scalable storage capacity from terabytes to petabytes of data. By retaining data in its original format, data lakes save organizations time that would have been used to define structures, create schemas, and transform the data. The ability to access data in its original format enables fast, flexible reuse of the data for a wide range of current and future use cases. Some of the vendors that provide technologies, platforms, and reference architectures for data lakes include Amazon, Cloudera, Google, IBM, Informatica, Microsoft, Oracle, SAS, Snowflake, Teradata, and Zalani. All in all, data lakes were designed in response to the limitations of data warehouses. Depending on the requirements, a typical organization will require both a data warehouse and a data lake as they serve different needs. Let's compare data lakes with data warehouses. When it comes to data, in a data lake, data is integrated in its raw and unstructured form. A data warehouse is different. Here, all data has already been processed and conformed to standards prior to loading to the data warehouse. Talking about schema when using data lakes, you do not need to define the structure and schema of the data before loading into the data lake. A data warehouse, on the other hand, requires strict conformance to schema, and therefore a schema needs to be designed and implemented prior to loading the data. How does data quality differ when looking at data lakes and data warehouses? In data lakes, the data might or might not be curated, for example, raw data, and data is agile and does not necessarily comply with governance guidelines. In comparison, the data in data warehouses is curated and adheres to data governance. Here, we are looking at users of data lakes and data warehouses. Data scientists, data developers, and machine learning engineers are the typical users of data lakes. Data warehouses, on the other hand, are mainly used by business analysts and data analysts. In this video, you learned that a data lake is a storage repository that can store large amounts of structured, semi-structured, and unstructured data in their raw or native format, classified and tagged with metadata. You do not need to define the structure and schema of data before loading into the data lake. Data lakes offer several benefits, such as storage for all types of data, scalable storage capacity, time savings, and flexible data reuse. And finally, you learned that data lakes can be used as a kind of self-serve staging area for a variety of use cases, including machine learning development and advanced analytics. Welcome to Data Warehouse Architecture Overview. After watching this video, you will be able to list use cases that drive data warehouse design considerations, describe a general data warehousing architecture and list its component layers, distinguish between general and reference enterprise data warehouse architecture, and describe reference architecture for an enterprise data warehouse platform. The details of the architecture of a data warehouse depend on the intended usage of the platform. Requirements can include report generation and dashboarding, exploratory data analysis, automation and machine learning, and self-serve analytics. Let's start by considering a general architecture model for an enterprise data warehouse, or EDW platform, which companies can adapt for their analytics requirements. In this architecture, you can have various layers or components, including data sources, such as flat files, databases, and existing operational systems, an ETL layer for extracting, transforming, and loading data, optional staging and sandbox areas for holding data and developing workflows, an enterprise data warehouse repository, Sometimes data marts, which are known as a hub and spoke architecture when multiple data marts are involved, and an analytics layer and business intelligence tools. Data warehouses also enforce security for incoming data and data passing through to further stages and users throughout the network. Enterprise data warehouse vendors often create proprietary reference architecture and implement template data warehousing solutions that are variations on this general architectural model. A data warehousing platform is a complex environment with lots of moving parts. Thus, interoperability among components is vital. Vendor-specific reference architecture typically incorporates tools and products from the vendor's ecosystem that work well together. Next, let's check out IBM-specific reference data warehouse architecture. Each layer of the architecture performs a specific function. The data acquisition layer consists of components to acquire raw data from source systems such as human resources, finance, and billing departments. The data integration layer, essentially a staging area, has components for extracting the data, transforming it, and loading it into the data repository layer. It also houses administration tools and central metadata. The data repository layer stores the integrated data, typically employing a relational model. The analytics layer often stores data in a cube format to make it easier for users to analyze it. And the final presentation layer incorporates applications that provide access for different sets of users, such as marketing analysts, users, and agents. Applications consume the data through web pages and portals defined in the reporting tool or through web services. IBM reference architecture is supported and extended using several products from the IBM InfoSphere suite. IBM InfoSphere Data Stage is a scalable ETL platform that delivers near real-time integration of all data types on-premises and in cloud environments. IBM InfoSphere Metadata Workbench provides end-to-end data flow reporting and impacts analysis and information assets in an environment that allows organizations to share easily, locate, and retrieve information from these systems. Use the built-in data flow reporting capabilities to monitor how IBM InfoSphere Data Stage moves and transforms your data. IBM InfoSphere Quality Stage, designed to support your data quality and information governance initiatives, enables you to investigate, cleanse, and manage your data. This solution helps you create and maintain consistent views of key entities, including customers, vendors, locations, and products. IBM DB2 Warehouse is a family of highly performant, scalable, and reliable data management products that manage both structured and unstructured data across on-premises and cloud environments. And finally, IBM Cognos Analytics is an advanced business intelligence platform that generates reports, scoreboards, and dashboards, performs exploratory data analysis, and even curates and joins your data using multiple sources. In this video, you learned that an architectural model for a general data warehousing platform includes data sources, ETL pipelines, optional staging and sandbox areas, an enterprise data warehouse repository, optional data marts, and analytics and business intelligence tools. Companies can modify general enterprise data warehouse architecture to suit their analytics requirements. Vendors offer proprietary reference architecture based on the general model, which they test for interoperability among components. And an IBM Enterprise Data Warehouse solution combines InfoSphere with DB2 Warehouse and Cognos Analytics. Welcome to Cubes, Rollups, and Materialized Views and Tables. After watching this video, you will be able to relate what a data cube is in terms of star schema. Discuss the terms slice, dice, drill up or down, roll up, and pivot in terms of data cubes. Describe what a materialized view is, and recall 2 use cases for materialized views. Let's use an example to illustrate the concept of a data cube. Here is a cube generated from an imaginary star schema for a sales OLAP, or Online Analytical Processing System. The coordinates of the cube are defined by a set of dimensions, which are selected from the star schema. In this illustration, we are only showing 3 dimensions, but data cubes can have many dimensions. We have the product categories corresponding to the items sold, the state or province the items were sold from, and the year these products were sold in. Now, the cells of the cube are defined by a fact of interest from the schema, which could be something like total sales in thousands of dollars. Here, the 243 indicates $243,000 for some given product, state, and year combination. There are many operations you can perform on data cubes, such as slicing, dicing, drilling up and down, pivoting, and rolling up. Let's go over some examples of these operations, starting with slicing. Slicing a data cube involves selecting a single member from a dimension, which yields a data cube that has one dimension less than the original. For example, you can slice this sales cube by selecting only the year 2018 from the year dimension, allowing you to analyze sales totals for all sales states and all products for the year 2018. Similarly, dicing a cube involves selecting a subset of values from a dimension, effectively shrinking it. For example, you can dice this sales cube by selecting only gloves, t-shirts, and jeans from the product type dimension, allowing you to restrict your view to just those product types. In Snowflake schema, you will find hierarchies or subcategories within some of your dimensions that you can drill into. Thus, for example, you can drill down into a particular member of the product category dimension, such as t-shirts, resulting in this view, which may include more specific product groups such as classic, slim fit, and regular fit. Drilling up is just the reverse process, which would take you back to the original data cube. Pivoting data cubes is straightforward. It involves a rotation of the data cube. In this case, the year and product dimensions have been interchanged while the state dimension has been fixed as is. Pivoting doesn't change its information content, it just changes the point of view you may choose to analyze it from. Rolling up means summarizing along a dimension. You can roll up a dimension by applying aggregations, such as count, min, max, sum, and average. For example, you could calculate the average selling price of classic, slim fit, and regular fit t-shirts by summing horizontally over the 3 U.S. states and dividing by 3. A materialized view is essentially a local read-only copy, or snapshot of the results of a query. They can be used to replicate data. For example, to be used in a staging database as part of an ETL process, or to pre-compute and cache expensive queries such as joins or aggregations for use in data analytics environments. Materialized views also have options for automatically refreshing the data, thus keeping your query up to date. Because materialized views can be queried, you can safely work with them without worrying about affecting the source database. Materialized views can also be set up to have different refresh options, such as never. They are only populated when created, which is useful if the data seldom changes. Upon request, manually refresh, for example, after changes to the data have been made, or scheduled refresh, for example, after daily data loads, and immediately, automatically refresh after every statement. Let's look at an example. Here is how you might create a materialized view in Oracle using SQL statements. Start by creating and naming a materialized view object called my_mat_view. Specify the refresh type as fast, which means incrementally refresh the data. Specify today as the start date, and refresh the view every day. The final statement selects all data from my_table_name. And here is how you might create a materialized view in PostgreSQL to replicate a table. Start by creating a materialized view object called my_mat_view. Specify some parameters and then specify the source tablespace, say tablespace_name. Select all rows and columns from table_name. Note, in PostgreSQL, you can only refresh materialized views manually using the refresh material view command. In DB2, materialized views are called MQTs, which stand for Materialized Query Tables. Here's an example from IBM's online documentation of creating a system-maintained immediate refresh MQT. The table, which is named EMP, is based on the underlying table's employee and department from the sample database. The table will be created according to the query formed by these SQL statements, which selects columns from both tables. The Data Initially Deferred clause means that data will not be inserted into the table as part of the Create Table statement, while the Refresh Immediate clause specifies that the query should refresh automatically. The Immediate Checked clause specifies that the data is to be checked against the MQT's defining query and refreshed. And lastly, the Not Incremental clause specifies that integrity checking is to be done on the whole table. A query executed against the EMP materialized query table shows that it is fully populated with data. In this video, you learned that a data cube represents a star or snowflake schema's dimensions as coordinates, plus a fact from the schema to populate its cells with values. Many operations can be applied to data cubes, such as drilling down into hierarchical dimensions, slicing, dicing, and rolling up. Materialized views can be used to replicate data or to pre-compute expensive queries. And finally, modern enterprise data warehouse tools, such as Oracle and DB2, allow you to automatically keep your material views up to date. Welcome to Facts and Dimensional Modeling. After watching this video, you will be able to define what facts are in context of data warehousing, define what a fact table is, define what dimensions are in context of data warehousing, define what a dimension table is, and describe an example of a fact and its dimensions. Data can be lumped into two categories, facts and dimensions. Facts are usually quantities which can be measured, such as temperature, number of sales, or millimeters of rainfall. But facts can also be qualitative in nature. Dimensions are attributes which can be assigned to facts. Dimensions provide context to facts, which makes facts useful. For example, a temperature such as 24 degrees Celsius all by itself is not meaningful information. Let's look at a familiar example. Here, we have a weather report obtained by Googling weather in Kuala Lumpur. The facts here are things like the temperature, humidity, probability of precipitation, and wind speed. Notice that these are all quantities. But there are other facts here, such as this icon, which means partly cloudy, or the statement clear with periodic clouds, and these other icons which indicate forecasted conditions, such as thunder showers. All of these non-numeric facts are examples of qualitative facts. To make sense of these facts, we need to provide context. Context is provided by dimensions, which includes things like the location, Kuala Lumpur, Malaysia, and the date and time, Tuesday at 3 a.m. The statement 24 degrees Celsius in Kuala Lumpur, Malaysia on Tuesday, August 17th at 3 a.m. means something. A fact table typically consists of the facts of a business process, and it also contains foreign keys which establish well-defined links to dimension tables. Usually, facts are additive measures or metrics, such as dollar amounts for individual sales transactions. A fact table can contain detail-level facts, such as individual sales transactions, or facts that have been aggregated, such as daily or weekly sales totals. Fact tables can contain aggregated facts and are called summary tables. For example, you could summarize sales transactions by summing overall sales for each quarter of the year. An example of a foreign key might be store ID. Accumulating snapshot fact tables are used to record events that take place during a well-defined business process. For example, suppose you have finished configuring a custom computer for yourself online and you have just placed your order. The order date and the order amount are recorded in a snapshot table by the manufacturer. A unique order ID is also assigned. Once your order is verified, your payment is processed. The amount paid and the date paid are then recorded. After payment verification, the computer specifications are sent to the manufacturing department. Once the computer is in production, the build start date is entered. And once the computer is built, the build end date is recorded. Finally, once your computer is ready to be sent, the ship date is recorded. All these fields are stored in a single row of the table, which is uniquely identified by the order ID. Now, a dimension is a variable that categorizes facts. Dimensions are called categorical variables by statisticians and machine learning engineers. Dimensions enable users to answer business questions. The main uses for dimensions in analytics include filtering, grouping, and labeling operations. For example, commonly used dimensions include names of people, products, and places, and date or time stamps. A dimension table, thus, stores the dimensions of a fact and is joined to the fact table via a foreign key. Some examples of various types of dimension tables include product tables, which describe products, such as make, model, color, and size. Employee tables, which describe employees, such as name, title, and department. Temporal tables, which describe time at the level of granularity or precision at which events are recorded. And geography tables for location data, such as country, state, city, and postal or zip code. Let us look at an example of a schema with both fact and dimension tables to help illustrate their relationships. We could have a fact table for recording sales at a car dealership. This table would store facts about each car sale, such as the sale date and sale amount, as well as a primary key, sale ID. For each sales transaction, we also need to record its dimensions, like the vehicle sold and the salesperson who sold it. The attributes of these dimensions, such as the vehicle make and model, or the salesperson's first and last name, are stored in separate vehicle and salesperson tables. However, we link them with the sales table by recording the vehicle ID and the salesperson ID as foreign keys in the fact table. This way, we typically end up with multiple dimension tables for each fact table. In this video, you learned that business data falls into two categories, facts and dimensions. Facts are usually numerical measures of business processes, such as sale amounts in dollars. Dimensions, such as sold by and store ID, categorize facts, such as who sold the product, when, and which store it was sold from. Dimensions are categorical variables that provide context for facts and are used for filtering, grouping, and labeling. And facts and dimension tables are linked together by foreign and primary keys. Welcome to data modeling using star and snowflake schemas. After watching this video, you will be able to describe star schema modeling in terms of facts and dimensions, describe snowflake schema as an extension of star schema, and distinguish star from snowflake schema in terms of normalization. Recall that a fact table contains foreign keys that refer to the primary keys of dimension tables. The idea of a star schema is based on the way a set of dimension tables can be visualized or modeled as radiating from a central fact table linked by these keys. A star schema is thus a graph, whose nodes are facts and dimension tables, and whose edges are the relations between those tables. Star schemas are commonly used to develop specialized data warehouses called data marts. Snowflake schemas are a generalization of star schemas and can be seen as normalized star schemas. Normalization means separating the levels or hierarchies of a dimension table into separate child tables. A schema need not be fully normalized to be considered a snowflake, so long as at least one of its dimensions has its levels separated. Let's look at some general principles you need to consider when designing a data model for a star schema. The first step involves selecting a business process as the basis for what you want to model. You might be interested in processes, such as sales, manufacturing, or supply chain logistics. In step 2, you need to choose a granularity, which is the level of detail that you need to capture. Are you interested in coarse-grained information, such as annual regional sales numbers, or maybe you want to drill down into monthly sales performance by salesperson? Next in the process, you need to identify the dimensions. These may include attributes such as the date and time and names of people, places, and things. The final consideration in designing star schemas is to identify the facts. These are the things being measured in the business process. Let's apply these considerations to a scenario. Imagine, for example, that you are a data engineer helping to lay out a data ops for a new store called A to Z Discount Warehouse. They would like you to develop a data plan to capture everyday POS or point of sales transactions that happen at the till where customers have their items scanned and pay for them. Thus, point of sale transactions is the business process that you want to model. The finest granularity you can expect to capture from POS transactions comes from the individual line items, which is included in the detailed information you can see on a typical store receipt. This is precisely what A to Z is interested in capturing. The next step in the process is to identify the dimensions. These include attributes such as the date and time of purchase, the store name, the products purchased, and the cashier who processed the items. You might add other dimensions like payment method, whether the line item is a return or a purchase, and perhaps a customer membership number. Now it's time to consider the facts. Thus, you identify facts such as the amount of each item's price, the quantity of each product sold, any discounts applied to the sale, and the sales tax applied. Other facts to consider include environmental fees or deposit fees for returnable containers. Now, you are ready to start building your star schema for A to Z Discount Warehouse. At the center of your star schema sits a point of sales fact table, which contains a unique ID called POS ID for each line item in the transaction, plus the following facts or measures: the amount of the transaction in dollars, the quantity or number of items involved, the sales tax, and any discount applied. There may be other facts to include, but these can be added later as you discover them. Each line item from a sales transaction has many dimensions associated with it. You include them as foreign keys in your fact table or as links to the primary keys of your dimension tables. For example, the name of the store at which the item was sold is kept in a dimension table called store, which is identified in the fact table by the value of the foreign store ID key, which is the primary key for the store table. Product information is stored in the product table, which is uniquely identified by the product ID key. Similarly, the date of the transaction is keyed by the date ID, which cashier entered the transaction is keyed by the cashier ID, and which member was involved is indicated by the member ID. This illustrates what a star schema might look like. Let's see how you can use normalization to extend your star schema to a snowflake schema. Starting with your star schema, you can extract some of the details of the dimension tables into their own separate dimension tables, creating a hierarchy of tables. A separate city table can be used to record which city the store is in, while a foreign city ID key would be included in the store table to maintain the link. You might also have tables and keys for the city, state, or province, and a predefined sales region for the store, as well as which country the store resides in. We've left out the associated keys for simplicity. We can continue to normalize other dimensions, like the product's brand and a product category that it belongs to, the day of week and the month corresponding to the date, plus the quarter, and so on. This normalized version of the star schema is called a snowflake schema, due to its multiple layers of branching which resembles a snowflake pattern. Much like pointers are used to point to memory locations in computing, normalization reduces the memory footprint of the data. In this video, you learned that the facts and dimensions tables, together with foreign and primary keys, are used to form star and snowflake modeling schemas. Design considerations for data modeling with star schema include identifying a business process, its granularity, and its facts and dimensions. Snowflake schemas can be described as normalized star schemas, where normalization involves separating dimension tables into individual tables defined by levels or hierarchies of the parent dimension and reduces storage footprint. Welcome to Staging Areas for Data Warehouses. After watching this video, you will be able to describe what a data warehouse staging area is, describe why a staging area may be used, and relate how a staging area is used as a first step for integrating data sources. What is a data warehouse staging area? You can think of a staging area as an intermediate storage area that is used for ETL processing. Thus, staging areas act as a bridge between data sources and the target data warehouses, data marts, or other data repos. They are often transient, meaning that they are erased after successfully running ETL workflows. However, many architectures hold data for archival or troubleshooting purposes. They are also useful for monitoring and optimizing your ETL workflows. Staging areas can be implemented in many ways, including simple flat files, such as CSV files stored in a directory and managed using tools such as Bash or Python, or a set of SQL tables in a relational database such as DB2, or a self-contained database instance within a data warehousing or business intelligence platform such as Cognos Analytics. Let us explore an example use case to illustrate a possible architecture for a data warehouse containing a staging area, which in turn includes an associated staging database. Imagine the enterprise would like to create a dedicated cost accounting online analytical processing system. The required data is managed in separate online transaction processing systems within the enterprise, from the payroll, sales, and purchasing departments. From these siloed systems, the data is extracted to individual staging tables, which are created in the staging database. Data from these tables is then transformed in the staging area using SQL to conform it to the requirements of the cost accounting system. The conformed tables can now be integrated or joined into a single table. And the final phase is the loading phase, where the data is loaded into the target cost accounting system. A staging area can have many functions. Some typical ones include integration. Indeed, one of the primary functions performed by a staging area is consolidation of data from multiple source systems. Change detection. Staging areas can be set up to manage extraction of new and modified data as needed. Scheduling. Individual tasks within an ETL workflow can be scheduled to run in a specific sequence concurrently and at certain times. There's also data cleansing and validation. For example, you can handle missing values and duplicated records. Aggregating data. You can use the staging area to summarize data. For example, daily sales data can be aggregated into weekly, monthly, or annual averages prior to loading into a reporting system. And normalizing data to enforce consistency of data types or names of categories such as country and state codes in place of mixed naming conventions such as Mont, MA, or Montana. A staging area is a separate location where data from source systems is extracted to. The extraction step therefore decouples operations such as validation, cleansing, and other processes from the source environment. This helps to minimize any risk of corrupting source data systems and simplifies ETL workflow construction, operation, and maintenance. And if any of the extracted data becomes corrupted somehow, you can easily recover. In this video, you learned that a staging area acts as a bridge between data sources and the target system and are mainly used to integrate disparate data sources and data warehouses. Staging areas can be implemented quite simply as a set of flat files in a directory and managed with scripts or as tables in a database. Staging areas decouple data processing from the source systems and thus help minimize risk of data corruption. And although they are often transient, staging areas can be held for archiving or troubleshooting purposes. Welcome to Verifying Data Quality. After watching this video, you will be able to describe data quality verification, identify why organizations verify data, list examples of data quality concerns, and outline a process for handling bad data. Data verification includes checking your data for accuracy, is your data correct, completeness, is there missing data, consistency, are fields consistently entered, and currency, is your data up to date? Data verification is about managing data quality and enhancing its reliability. High-quality data enables successful integration of related data and its complex relationships. Data verification also provides you with the complete and connected view of your organization, data that is ready for advanced analysis, statistical modeling and machine learning, and ultimately more confidence in your insights and decision-making. Unfortunately, data quality is not a top concern among the daily chaos of running a company. According to Harvard Business Review, IBM's 2016 estimate of the yearly cost of poor data quality in the U.S. alone was over $3 trillion. Let's identify data quality concerns that organizations contend with. The first is accuracy. Accuracy includes ensuring a match between source data and destination data. How can accuracy become an issue? Data migrating from source systems often contains duplicated records. When users enter data manually, typos can find their way into the data records, yielding out-of-range values, outliers, and spelling mistakes. Sometimes large chunks of data become misaligned, causing data corruption. For example, a CSV file might contain a legitimate comma, which the new system can misinterpret as a column separator. Another data quality concern is completeness. Data is incomplete when the business finds missing values, such as voids or nulls in fields that should be populated, or haphazard use of placeholders such as 999 or -1 to indicate a missing value. Entire records can also be missing due to upstream system failures. Consistency is another important data quality concern. Are there deviations from standard terminology? Are dates entered consistently? For example, year, month, day, and month, day, year formats are incompatible. Is data entered consistently? For example, Mr. John Doe and John Doe might refer to the same person in the real world, but the system will see them as distinct. And are the units consistent? For example, you are expecting kilograms, but you might have entries based on pounds. Or you are expecting dollar amounts, but you might have entries based on thousands of dollars. Lastly, currency is an ongoing data quality concern for most businesses. Currency is about ensuring your data remains up to date. For example, you might have dimension tables that contain customer addresses, some of which might be outdated. In the US, you could check these against a change of address database and update your table as required. Another currency concern would be name changes, as customers can change their names for various reasons. Determining how to resolve and prevent bad data can be a complex and iterative process. First, you'll implement rules to detect bad data. Then you'll apply those rules to capture and quarantine any bad data. You might need to report any bad data and share the findings with the appropriate domain experts. You and your team can investigate the root cause of each problem, searching for clues upstream in the data lineage. Once you diagnose each problem, you can begin correcting the issues. Ultimately, you want to automate the entire data cleaning workflow as much as possible. For example, you need to validate the quality of data in the staging area before loading the data into a data warehouse for analytics. You determine that data from certain data sources consistently has data quality issues, including missing data, duplicate values, out-of-range values, and invalid values. Here's how an organization might manage and resolve these issues. First, write SQL queries to detect these issues and test for them. Next, address some of the quality issues that you've repeatedly identified by creating rules for treating them, such as removing rows that have out-of-range values. Create a script that runs queries to detect data quality issues that happen during the nightly loads to the data warehouse. This script applies corrective measures and transformations for some of these known issues. Next, create a second script that automates the script you created in Step 3. After the data is extracted from the various data sources, this script automatically runs the prior script's SQL data validation queries every night in the staging area. The script you created in Step 3 generates a report of any remaining issues that could not be automatically resolved. The administrator can review this report and address the unresolved issues. Some of the leading vendors and their tools for data quality solutions include IBM InfoSphere Server for Data Quality and IBM Data Refinery, Informatica Data Quality, SAP Data Quality Management, SAS Data Quality, Talend Open Studio for Data Quality, Precisely Spectrum Quality, Microsoft Data Quality Services, Oracle Enterprise Data Quality, and an open source tool called OpenRefine. Each of these solutions has its own strengths. Let's look at one of these solutions. The IBM InfoSphere Information Server for Data Quality is an example of a product that can help you perform data verification in a unified environment. InfoSphere Information Server for Data Quality enables you to continuously monitor the quality of your data and keep your data clean on an ongoing basis, helping you turn your data into trusted information. In addition, the IBM InfoSphere Information Server for Data Quality comes with built-in end-to-end data quality tools to help you understand your data and its relationships, monitor and analyze data quality continuously, clean, standardize, and match data, and maintain data lineage, which is the history of the data's origin and what happened to the data along the way. In this video, you learned that data verification includes checking your data for accuracy, completeness, consistency, and currency. Data verification is about managing data quality, enhancing data reliability, and maximizing data value. Determining how to resolve and prevent bad data can be a complex and iterative process. And enterprise-grade tools, such as IBM InfoSphere Information Server for Data Quality, can help you perform data verification in a unified environment.
Welcome to Populating a Data Warehouse. After watching this video, you'll be able to describe populating a data warehouse as an ongoing process. List the main steps for populating a data warehouse. List methods for change detection and incremental loading. Manually create and populate tables for a sales star schema. Recall the periodic maintenance required to keep your data warehouse running smoothly. Populating the enterprise data warehouse is an ongoing process. You have an initial load followed by periodic incremental loads. For example, you may load new data every day or every week. Rarely, a full refresh may be required in case of major schema changes or catastrophic failures. Generally, fact tables are dynamic and require frequent updating, while dimension tables don't change often. For example, lists of cities or stores are quite static, but sales happen every day. Many tools are available to automate the ongoing process of keeping your data warehouse current. Databases like DB2 have a load utility that is faster than inserting a row at a time, and loading your warehouse can also be a part of your ETL data pipeline that is automated using tools like Apache Airflow and Apache Kafka. You can also write your own scripts, combining lower-level tools like Bash, Python, and SQL to build your data pipeline and schedule it with cron. And InfoSphere Data Stage allows you to compile and run jobs to load your data. Before populating your data warehouse, ensure that your schema has already been modeled, your data has been staged in tables or files, and you have mechanisms for verifying the data quality. Now you're ready to set up your data warehouse and implement the initial load. You first instantiate the data warehouse and its schema, then create the production tables. Next, establish relationships between your fact and dimension tables. And finally, load your transformed and clean data into them from your staging tables or files. Now that you've gone through the initial load, it's time to set up ongoing data loads. You can automate subsequent incremental loads using a script as part of your ETL data pipeline. You can also schedule your incremental loads to occur daily or weekly, depending on your needs. You will also need to include some logic to determine what data is new or updated in your staging area. Normally, you detect changes in the source system itself. Many relational database management systems have mechanisms for identifying any new, changed, or deleted records since a given date. You might also have access to timestamps that identify both when the data was first written and the date it might have been modified. Some systems might be less accommodating, and you might need to load your entire source to your ETL pipeline for subsequent brute force comparison to the target, which is fine if the source data isn't too large. Data warehouses need periodic maintenance, usually monthly or yearly, to archive data that is not likely to be used. You can script both the deletion of older data and its archiving to slower, less costly storage. Let's illustrate the process with a simplified example of manually populating a data warehouse with a star schema called sales. We'll assume you've already instantiated the data warehouse and the sales schema. Here's a sample of some auto sales transaction data from a fictional company called Shiny Auto Sales. You can see several foreign key columns such as Sales ID, which is a sequential key identifying the sales invoice number, EMPNO, which is the employee number, and Class ID, which encodes the type of car sold, such as small SUV. Each of these keys represents a dimension that points to a corresponding dimension table in the star schema. The date column is a dimension that indicates the sale date. The amount column is the sales amount, which happens to be the fact of interest. This table is already close to the form of a fact table. The only exception is the date column, which is not yet represented by a foreign date ID key. Let's use PSQL, the terminal-based front end for PostgreSQL, to illustrate how you can create your dimension tables using the salesperson dimension as an example. Use the Create Table clause to create the dim salesperson table with the sales schema along with salesperson ID as a serial primary key, salesperson alt ID as the salesperson's employee number, and finally, a column for the salesperson's name. Now you can start populating the dim salesperson table row by row. You use an Insert Into clause on the sales.dimsalesperson table, specifying the salesperson alt ID and salesperson name columns, and begin inserting values such as employee number 680, Cadillac Jack. You would similarly create and populate tables for the remaining dimensions. You can enter the SQL statement, select star from sales.dim salesperson limit 5 to view your salesperson dimension table, and see that everything seems to be correctly populated, such as record 1, employee number 617, and salesperson name Go-Kart Joe. Now it's time to create your sales fact table. Using Create Table with sales.factAutoSales as the table name, transaction ID as the primary key with big serial type, and the various foreign keys such as sales ID and auto class ID, and finally, the fact of interest amount as type money. Next, you proceed with setting up the relations between the fact and dimension tables of the sales schema. For example, you can apply the alter table statement and the add constraint clause to the sales.factAutoSales fact table. To add KV auto class ID as a foreign key relating auto class ID to the same column name in the sales.dim auto category table using the references clause. You would then use the same method to set up the relations for the remaining dimension tables. After defining all the tables and setting up the corresponding relations, it's finally time to start populating your fact table using the sales data that you started with. You can use the Insert Into statement on sales.factAutoSales, specifying the column names Sales ID, Amount, Salesperson ID, Auto Class ID, and Sales Date Key, and entering rows such as 1629, 42,000, 2, 1, and 4, which you would obtain using the auto sales data. You can view the auto sales fact table by entering the SQL statement select star from sales.factautosales limit 5 to display its first 5 rows. Here you see the dollar amounts for individual auto sales, the primary key called transaction ID, and the remaining columns, which are foreign keys that you set up. In this video, you learned that populating an enterprise data warehouse includes initial creation of fact and dimension tables and their relations and loading of clean data into tables. Populating the enterprise data warehouse is an ongoing process that starts with an initial load followed by periodic incremental loads. Fact tables are dynamic and require frequent updating, while dimension tables are more static and don't change often. And you can automate incremental loading and periodic maintenance of your data warehouse using scripting or built-for-purpose data pipeline tools.
Welcome to Querying the Data. After watching this video, you will be able to interpret an entity relationship diagram, or ERD, for a star schema and use the relations between tables to set up queries. Create a materialized view by denormalizing or joining tables from a star schema, and apply the cube and rollup options in a group by clause to generate commonly requested total and subtotal summaries. Cube and rollup operations generate the kinds of summaries that management often requests. These summaries are much easier to implement than the multiple SQL queries that are otherwise required. Materialized views conveniently enable you to create a stored table so you can refresh on a schedule or on demand. When the view is complex, requested frequently, or is run on large datasets, consider materializing the view to help reduce the load on the database. Because data is pre-computed, querying materialized views can be much faster than querying the underlying tables. Combining cubes or rollups with materialized views can enhance performance. You can even follow up by materializing the cube or rollup. Consider the following scenario. You have the task of creating some live summary tables for reporting January sales by salesperson and automobile type for Shiny Auto Sales. Begin by understanding the existing star schema in their data warehouse called SASDW based on PostgreSQL. Then explore relevant Shiny Auto Sales data by querying the tables from the sales star schema in the SASDW warehouse. After exploring the schema, you decide to create a materialized view as a staging table. Creating the view as a staging table provides you with the data you need while minimizing your impact on the database. You can incrementally refresh the data at will during off-peak hours. You start a PostgreSQL session and generate an entity relationship diagram, or ERD, which represents the sales star schema implemented within the Shiny Auto Sales data warehouse, SASDW. Then you locate the central fact table named Fact Auto Sales. This table contains the amount column, which is the measure you need. You also spot the 3 foreign keys in the sales fact table: sales date key, auto class ID, and salesperson ID. These keys link respectively to the date dimension table, which contains dates and related values, such as the day of the week, month name, and quarter. The auto category dimension table, which includes the auto class name and the Boolean is new column. And finally, the salesperson dimension table, which contains the salesperson's name. In this example, you are using PostgreSQL. Let's assume you already started up the terminal-based front end to PostgreSQL, or PSQL, and connected to the SASDW data warehouse. Notice the command prompt contains the name of the data warehouse you are connected to, SASDW. Starting with the auto sales fact table, you'll enter the SQL statement, select star from sales.fact auto sales, limit 10, to display its first 10 rows. Here, you see the dollar amounts for individual auto sales, but the remaining columns are primary and foreign keys, which don't have any direct meaning for you yet. However, you notice that the sales ID values are sequential, but the numbering starts at 1,629 instead of 1. That's because Shiny Auto Sales has provided you with access to a windowed subset of their data. Next, you query the auto category dimension table. Now, you can see meaningful names for various automobile classes, such as truck and compact SUVs. You notice duplicate entries for the truck class and wonder why they exist. When you look more closely, you realize the duplicate entries exist because of the distinct subclasses for new and used trucks. Similarly, you generate a view for the salesperson dimension table and find 8 distinct salesperson names, including Go-Kart Joe and Jane Honda. So far, so good. Finally, you view the date dimension table. You notice the dates only go back to January 1, 2021. Your contact at Shiny Auto Sales informs you that she will provide you with more detail later, and that for now you can work with a smaller data set while you develop your queries. The date table contains potentially useful date elements, such as the day of the week, month name, and quarter name. At this stage, it would be more convenient to have a table of data that contains the dimensions you need with human interpretable columns rather than just keys. Essentially, you want to create a denormalized view of the data by joining the dimensions back to the fact of interest. You proceed by selecting the date, auto class name, is new, salesperson name, and amount columns from their tables, and joining each dimension onto the amount fact using an inner join on the corresponding keys. Next, why not capture the view as a materialized view called denormalized sales, or DN sales for short. Then you can reuse the materialized view for different queries without having to recreate your work. You accomplish this task using the clause create materialized view DN sales as, followed by the same query you used to generate the denormalized view. Type select star from DN sales limit 10 to display your resulting materialized view. Now you have a tidy human-readable time series of sales data available for further analysis. For example, you can see that Cadillac Jack sold a new mid-size SUV on January 5th for $26,500. Next, you want to apply cube and roll-up operations to your denormalized materialized view. Let's see the cube results. Here, you select the auto class name, salesperson name, and the sum of the sales amounts from DN sales where is new is set to true. Finally, group the generated cube by the auto class name and salesperson name. The output looks like this. The first row has no entries in the dimensions columns, which means all. Thus, the value of $366,076 represents the total sales of all new cars. The next block of records has both dimension columns populated. So, for instance, you can read the total sales of new midsize SUVs by Go-Kart Joe, which is $32,099. Similarly, the last two blocks summarize new auto sales by class and by salesperson. Now, you'll apply a roll-up instead of a cube operation. You decide to keep the query the same as the previous query, except that you replace cube with roll-up. Here's what the resulting view looks like now. You have 5 fewer rows with the roll-up result than cube, resulting in 13 rows instead of 18 rows. The only difference in this result is that you don't have the total sales amount by salesperson summary. While cube generates all possible permutations of the group by columns, roll-up only looks at the single permutation defined by the columns order listed in the roll-up call. In this video, you learned that cube and roll-up summaries on materialized views provide powerful capabilities for quickly querying and analyzing data in data warehouses. Cube and roll-up operations generate the kinds of summaries grouped by dimensions that management often requests. You can denormalize star schemas using joins to bring together human interpretable facts and dimensions in a single materialized view. And you can create staging tables from materialized views, which you can incrementally refresh during off-peak hours. Welcome to Introduction to Analytics and Business Intelligence Tools. After watching this video, you will be able to define analytics, describe how business intelligence tools have changed analytics processing and results, outline the purpose of analytics and business intelligence tools, define what an analytics or business intelligence tool is, and identify several analytics and business intelligence tools. Analytics is the systematic compilation and dissection of data, statistics, and operations research to build models to make better decisions. Compute storage, processors, and memory capabilities have significantly increased speed, capacity, and affordability. The data warehousing solutions available now store large volumes of data with low latency. These exponential increases in both capacity and speed for storage, processors, and memory enable organizations to now process petaflops of data with swift turnaround times. When more data is available, analytics are more accurate. Organizations can use BI tools' built-in expertise to analyze data and find patterns using machine learning based on statistical modeling. Today's analytical tools have reduced the time to churn data so much that results are now almost real-time. These analytical outcomes can be descriptive, prescriptive, or predictive. Descriptive analytics provide insight into the past. Predictive analytics provide insight into what could happen in the future. In contrast, prescriptive analytics provide insight into what actions an organization should take to create a specific outcome in the future. Business intelligence tools, or BI tools, enable data preparation, data mining, data management, and data visualization. Implementing BI tools is much like solving a puzzle to gain a more comprehensive picture of your organization. BI tools help organizations focus on the what and the why. Businesses use their data to discover what is happening and determine what triggered a specific outcome. BI tools as highly evolved software apply statistics and operations research as part of the process of creating inherent intelligence. BI tools also help organizations harness the power of descriptive, diagnostic, predictive, and prescriptive analytics for operational and strategic decisions. Users can analyze business operations through dashboarding, reporting, and self-serve analytics based on historical, current, and projected data to transform data into business opportunities. There are many solutions available in the market that empower organizations with the ability to perform advanced analytics. Some of the well-known players in the market are IBM Cognos Analytics, which integrates Watson Analytics that leverages IBM's artificial intelligence and natural language processing. Microsoft Power BI, well known for its secure insights. Tableau is known for powerful visualizations. Oracle Analytics Cloud, known for its conversational analytics. SAP Business Objects, known for its intelligent analytics. And Tibco Spotfire offers scalability for small and large organizations. IBM has invested more than $25 billion since 2005 to grow its analytics business. Cognos Analytics is IBM's AI-fueled business intelligence and analytics software that supports the entire data analytics lifecycle from discovery to operations. In this video, you learned that analytics is building models with data to make better decisions. Business intelligence is a technology that enables data preparation, data mining, data management, and data visualization. The software market offers many business intelligence tools, and IBM Cognos Analytics is one of the top BI solutions available based on AI.
In this video, we're going to cover a couple of things. The first is a quick overview of what Cognos Analytics is, and we're going to show you how to sign up for the trial. Cognos Analytics is a multifaceted tool, allowing you to perform both Mode 1 and Mode 2 type of analysis all in one product. It contains a number of different tools, such as the ability to model your data, explore your data, create compelling advanced analytic visualizations like our key driver analysis, display natural language generated based off of your data, and create reports which are specific and tailored to your individual users, either through filters or through the ability to create bursts. We also have the ability to create fantastic dashboards, which will be the main focus of this particular course. Now to sign up for the trial, we're going to go to the ibm.biz/try_cognos. If you already have an account, you can log in here and you'll simply have to fill out part of this form. If you don't, then we'll go ahead, fill out this form quickly, and the key one to take note of is to select a data center which is close to you in your particular geography. Now the system is being spun up for us and we can go ahead and actually launch this directly from this workflow. Now that you're in, you can go ahead and either manage your subscription through this button, or alternatively, you can always re-access the system through this URL. In the next video, we'll take you through a little bit around how to navigate and use Cognos and its dashboard capabilities. In this particular video, we'll cover off how we can upload spreadsheets, general navigation in Cognos Analytics, how to start a new dashboard, using dashboard templates, as well as navigating within the Cognos Analytics dashboard environment. There are two main navigation areas for Cognos Analytics, along the left-hand side as well as along the top. These will change and update based on the area you're in the product. Now for today, while Cognos can connect to a number of databases, we're going to start with simply uploading an Excel file. Now we can do this in one of two ways. We can come to the new, select upload files, and navigate to find the file in question. Alternatively, what we can do is we can drag and drop the file onto our main landing page here and have it take us directly into the experience that we're looking to do. In our case here, dashboard. Now you'll notice that this says that uploaded content will land in my content, which is up there on the left-hand navigation. Whether you do it from here or through the plus and upload, it'll still land in the same place. Once in my content, it can be taken, moved around into a shared area within team content. As the file uploads here, you'll notice that we see something that says analyzing. This allows us to interrogate the data, get an understanding of what's in the data, in order to be able to help make some better assumptions and decisions for you as we look to build out content. The first thing we'll do as we go to build a dashboard is to select a template. You'll see a number here, and based on what you're trying to achieve, how many visualizations and what types, you may want to select something specific. In this case, I'll choose one that has 4 and 1 larger space. Once we're in the dashboard, we'll notice that the pane with our uploaded file column headers is displayed. There's a few other things that we want to highlight here in terms of navigation to help you with the experience here in Cognos Analytics. Our second pin down here allows you to pin different visualizations for reuse in other dashboards across the system. We'll come back to our assistant in a future video. This allows you to ask questions in natural language and have the system tell you a little bit about your data as well as provide some visualizations. The next system here is our view of all the different visualizations we support in the dashboard, as well as the ability to upload your own custom visualization should we not have one that meets your needs. The final one here is our additional widgets, whether that's text, images, video, hyperlinks, or any of these shapes that are viewed here. In the next video, we'll dive a little bit deeper into how specifically to create dashboards. In this video, we'll cover off creating some simple dashboards in Cognos Analytics. We'll cover off a variety of different methods for creating a visualization, whether it's through our automatic generation, manually populating slots, or using our assistant. We'll also cover off how you can filter within a Cognos Analytics dashboard. As I mentioned, as the data was uploaded, we took a look at the data and tried to understand what types of data were included. And that's denoted by the icon in front of each of these elements. Now, in the case of order ID, we actually want to switch this up and change the properties from a measure to an identifier. With that done, let's go ahead and start to create some visualizations. So I can simply grab from my tree and drag it onto the canvas. Now in this case, if I drop on top of the box, what it'll do is it'll fill the space available as denoted by the template. Next, let's look at the number of orders that we've had by counting the number of order IDs that we have. Now in this case, it determined the best visualization for an identifier to be a list. We can go ahead and take a look at what other recommended visualizations, in this case there aren't any, but we know we want to turn this into a summary, so we can just go and manually select it. Next up, let's look at the quantity ordered, and we'll finally finish with the average sale. So in this case, I'll drag sales onto the canvas, but what I'll do is I'll change our summarization from sum to average. And so just like that, I now have a few KPIs to be able to monitor and track. The other way we can start to create visualizations is by selecting the specific visualization we want and dragging it onto the canvas. In this case, I'm interested in looking at our sales across the world based on countries. So in this case, I can find country. Alternatively, if I have a lot of data, I can simply start to type at the top and I'll see country comes to the surface. As we said, we wanted to take a look at sales. In this case, we look specifically at country, but as you can see, we can go further down in terms of latitude and longitude. Now with this, I can manually drag and drop to make this as big or as small as I want, and you'll see that we show percentages of how much real estate it's actually taking up. Of course, each of our visualizations has a number of properties. We won't get into those in too much detail, but if there's something that you're looking to do, take a look in the properties and it's likely there. The final way that we'll show creating visualizations is through our assistant. Now in this case, I may have an idea of what I want to look at, or I may not. If I don't, I can simply ask it to suggest questions. This will offer up some insight that I may not have been thinking about. In this case, we'll keep it simple. We'll just look at which product line has the top sales. With a click, I'm now presented with the visualization as well as alternatives based on that particular visualization. If I'm happy with a view, I can simply drag and drop this onto my canvas, and it now becomes a visualization alongside the others. I can continue to resize this. Now, all of our dashboards are designed and meant to be interactive. So in this case, if I were interested in seeing the rest of my dashboard through the specific lens of classic cars, I can click on classic cars and you'll see that all my visualizations are now updating specifically with the filter of classic cars. Now this is one way that I can do it, and I can do it multiple clicks, or alternatively, I can take a particular field and drop it in. If I were perhaps interested in a particular status, I could drag this into the All tabs, or if I just wanted to be specific to this tab, in here. Now with this, I'll be able to choose one or many. In this case, maybe we want to take a look at how much we have in the on hold status. So with that, you'll see again, all of these have been updated to reflect simply the on hold. So it looks like from a worldwide view, we only have holds in a couple of countries, which is positive. In the next video, we'll delve deeper into a few of the more advanced capabilities of the dashboard. In this video, we're going to cover a few of the more advanced capabilities in Cognos Analytics dashboards. We'll cover how to create calculations, how to leverage navigation paths, how to do excludes from visualizations, as well as how to set top-bottom on a visualization. Much like Excel, our dashboard can create calculations. We list out a number of different options here that you can take a look at, or alternatively, you can simply start typing and we'll offer up suggestions. Now in this case, we're interested in looking at our MSRP minus the price that we sell each unit for to give us a margin calculation. Now this calculation is treated exactly the same as any of our other fields that we have in here. So in this case, let's select our margin and we'll look at product line and bring that in. Now in this case, we can see that trains is not doing very well. It's actually a negative margin for us. Now we may want to drill into this a little bit more. So we can create what we call navigation paths. In this case, I can choose any field from my data to be able to drill up and down on. In this case, we want to start with product line, and perhaps we want to see customers, and ultimately if there are specific orders. Now I can right-click on trains, and I can start to drill down. In this case, I can see that we have a few offenders who are in the negatives when we look at this particular field. So if we go ahead and look at something like mini gifts, again, we can drill down a little bit further to see that while they have one which is positive, their other ones are in the negatives. Let's take another look at something a little bit different. So if we were to look at sales by status and by product line. Now in this case, we're still filtered on trains, so we may want to go back and navigate up. In this case, we're still filtered on just trains. So let's unclick that to get back to our initial starting point. Now in this case, we can see that our shipped is really dramatically having an impact on this. So we can go ahead and we can choose to exclude our shipped items. Now we get a much better view of everything else that's going on for the other statuses. Another thing that we could do is if we have a large number of data points, in this case, perhaps customer sales, customer name and sales, we may want to filter down on only our most important ones. So in this case, I can come to sales, right click, and I can ask it to show us a top X number. In this case, by default, we have 10. So now we can see these are our top 10 customers. And one last one, just for fun, we can actually create infographics on the fly. So in this case, if I've got sales, I can take any one of my shapes here, perhaps a piggy bank, drop it on top, and just like that, we've now created an infographic.
Welcome to accessing your data warehouse using IBM Cognos. After watching this video, you will be able to describe the steps involved in accessing a database or data warehouse from Cognos Analytics, create an interactive dashboard using data in the data warehouse, and add multiple visualizations to the dashboard. In addition to files and static datasets, you can use Cognos Analytics to access a variety of databases and data warehouses, both on the cloud and in your enterprise, including IBM DB2 Warehouse, Amazon Redshift, Oracle, Microsoft SQL Server, MongoDB, MySQL, PostgreSQL, Snowflake, and others. First, identify the source databases, including schemas and tables, and obtain their connection credentials. Next, within Cognos Analytics, you'll create data server connections to the selected databases. And then, for each connection, create data modules for the selected tables. Next, create a dashboard and add the data modules as sources. And then, drag columns from the data module onto the dashboard canvas. Let's see these 5 steps in action. For this demo, you will use an IBM DB2 on Cloud database as the source data warehouse. First, you need to obtain the service credentials to connect to the database from the DB2 instance page by clicking New Credential. Now you need to name the service credential, set the role to Manager, and click Add to add the service credential. Scrolling down, you can see the service credential you just created displayed within the service credentials list. Click the credential drop-down arrow to view the credentials details. Here's a snippet of the service credential details. Copy the username, password, and the JDBC URL. You will need to replace the placeholder values for the username and password in the JDBC URL with actual values. Remember to remove the angle brackets. Next, let's identify and preview the data, that is, the schema and tables that you need for the Cognos dashboard. Under Manage, click Go to UI. This action opens the page where you can view, edit, and administer the DB2 instance. Within the DB2 UI, click the data icon, select the schema, and select the table you want to use for your dashboard in Cognos Analytics. Select the Customer Loyalty table. Here, you are previewing the Customer Loyalty table in the LFN 96733 schema. Viewing your table provides ideas about the data attributes you can visualize. Now that you have the database credentials and identified the data you want to visualize, go to the Cognos Analytics webpage, click the hamburger menu, and then Manage. You'll see several management options, but your task is to click Data Server Connections to connect with a data server. Click the plus icon to view the data warehouse options that you can connect to using Cognos. Next, click IBM DB2. Now click the option to connect anonymously and paste the JDBC connection string you copied from the DB2 instance administration page. Replace the username and password with your DB2 service credentials, and click Test to ensure you have a successful data connection. If the test was successful, you'll see success with a green checkmark icon. You can then name the connection. Here the connection is named MyDB2. Click Save. Next, you'll load the schema. Go to the Schema tab and click the three dots next to the schema you want to load. Then click Load Metadata. This action takes a few seconds while Cognos fetches and loads the metadata from the DB2 instance. Once the metadata is loaded, you'll see a green checkmark next to the schema name. Now that you have connected to the DB2 instance, you create a new data module that will link to the source data. This action opens a page where you can select the data source. Click the Data Servers icon in the left pane. Then click MyDB2, which is the connection you previously created. Here, click the schema you want to use and click OK. When the new module opens, click the table name. Cognos will open the table and you can view the data. Click the File icon to save the table. Give the data module an applicable name. Here, the data module is named My Customer Loyalty Module and is saved within the My Content folder. Click Save. Now that the data module is created, you will use it to create your dashboard. On the IBM Cognos Analytics menu, click New and then click Dashboard. You can select the tabbed or infographic layout with multiple template options in each. For this demo session, you click this template and then click Create. Click Select a Source to choose the data module to use for the dashboard. In the dashboard window, click the My Customer Loyalty data module in the Name column as your source, and then click Add. In the left pane of the My Customer Loyalty data module, drag the attributes that you want to see onto the dashboard. In this example, the quantity sold is selected. You can see the total quantity sold along with the title, which is the field label by default. You can double-click the label to change or format the text. You can also adjust the attribute's length, width, and position based on your design requirements. Next, drag the attributes into the tabbed area and render them as a bar plot. The attributes are rendered as a bar plot showing the sale for each product line over the years. You can adjust the size and position of the tab, and you can add a title and format it like the quality sold attribute. For the third tab, let's drag country below quantity sold to visualize regional sales. The world map appears. You can adjust the size of the region based on your needs. Let's add some attributes to the map. You want to add quantity sold so that you can visualize regional sales. Now, when you click a particular region, you can see the bar graph, and the quantity sold is updated as per the selected region. Here is a glimpse of the finished dashboard. Remember to save your completed dashboard with an appropriate link. Cognos makes it easy for you to share the finished dashboard as a viewable link. In this video, you learned that you can create dashboards and reports in Cognos Analytics using various data sources, including flat files, databases, and data warehouses. Accessing a database in Cognos requires a data server connection and a data module. A data server connection establishes a connection to the database, and a data module is a container or link to specific tables and database objects. You can add a data module to a dashboard just like any other source and use its fields and columns to create visualizations. And Cognos Analytics offers a variety of templates and visualization options to create interactive dashboards using data from data warehouses.